Hello, welcome to MR-CFD. This video presents analysis and discussion of the results of the CFD product thermal analysis in a storage tank in ANSYS Balloon software. Let's discuss pressure distribution. The pressure counter shows a relatively uniform high pressure region in the lower part of the tank, with a gradual decrease towards the outlet at the top. This pressure gradient drives the flow upwards and towards the outlet. A localized low-pressure area is observed near the outlet, consistent with the acceleration of flow as it exceeds the tank. This pressure drop could be significant for pump sizing and system design considerations. Let's discuss temperature distribution. The temperature contour displays a clear stratification of fluid temperatures within the tank. The left side shows higher temperatures, while the right side exhibits lower temperature. This distinct separation suggests limited mixing between the two inlet streams, which could be intentional for certain applications or problematic if homogeneous temperature distribution is desired. A mixing zone is observed in the central region, particularly near the outlet. This indicates that some thermal mixing occurs as the fluids converge towards the exit. Speaking of velocity distribution, the velocity vector and contour plots reveal a complex flow pattern within the tank. Two distinct inlet streams are observed which converge towards the central outlet at the top of the tank. The maximum velocity is observed near the outlet, indicating a significant acceleration of the fluid as it exits the tank. Large recirculation zones are evident in the upper corners of the tank, characterized by low-velocity regions. These zones may lead to potential dead spots or areas of poor mixing, which could be problematic for certain applications. The central region of the tank shows a higher velocity, indicating the primary flow path from the inlet to the outlet. This pattern suggests efficient fluid transport through the center of the tank. Now we want to see how turbulence kinetic energy is distributed. The turbulence kinetic energy contour reveals areas of high turbulence, particularly where the two inlet streams meet and along their path to the outlet. The maximum turbulence kinetic energy is observed in the central region, indicating intense mixing in this area. Lower turbulence is seen in the corner recirculation zones and near the walls, which aligns with the velocity distribution observations. This variation in turbulence levels could lead to non-uniform mixing within the tank. This CFD analysis provides valuable insights into the thermal and fluid dynamic behavior within the storage tank, serving as a foundation for potential design optimizations and operational strategies. The results demonstrate the complex interplay between velocity, turbulence, pressure, and temperature fields, highlighting the importance of CFD in designing and analyzing such systems. The dual inlet design effectively creates a controlled mixing zone near the outlet, allowing for temperature regulation of the exceeding fluid. The pressure distribution indicates a well-designed flow path from inlet to outlet, but the localized low-pressure area near the outlet should be considered in the overall system design. For applications requiring more uniform temperature distribution, we can consider internal structures or change the inlet configurations to promote better mixing throughout the tank. Further studies could involve transient simulations to understand the time-dependent behavior of the system, particularly for startup and shutdown scenarios. Hope this video is helpful for you. To benefit from MR-CFD services including simulation, consultation, and training, visit our website www.mrcfd.com or contact us via info@mrcfd.com.